so these, as you know, this is where we were last time on this particular slide. All right, so we're really going to concentrate on these times here, the quarks, which are the building blocks of protons and neutrons, leptons, which are electrons. The electrons are one of the fundamental. Electrons, you can't break electrons into other things. They're just, but protons and neutrons you can break up into quarks. Anyhow, and then there's the nuclear era, and then there's the atomic era, and then the galactic era, and the stellar era, and so forth. All right, so we're gonna get into this now. All right, so so this is this idea of freezing out. I want us to explore that just a little bit. As far as particles go, okay, this is the modern view of force, of the forces, of the fundamental forces, right? So it doesn't really matter whether it's the electric force, the weak nuclear force, or the strong nuclear force. Gravity, we think, operates this way, although we haven't been able to incorporate gravity into the quantum world. So this is basically a quantum view of how particles interact through forces. All right, but see, the thing is that it's not really through forces; it's through an exchange particle. And for example, for the exchange particle, if you have two charged particles, particle 1 and particle 2 are charges. Let's say, an electron and another electron. It doesn't even have to be opposite charges or anything like that, or an electron and a proton. The exchange particle for so what I'm talking about is the general category is called particle physics, by the way. It's pretty amazing that particle physics, the study of the very small, has a whole lot to do with the astronomy of the early universe, so anyhow, that's why we're kind of studying this right now. So let's say particle 1 has a certain charge, and a negative charge, it doesn't really matter what it is, and the other has a charge. It could also be a negative charge. So what the exchange particle is between when it's the electric charge, when it's the electric force, the exchange particle is called a photon, right? I mean, nothing mysterious there, right? That's a particle that that we've been talking about for a long time. But now, instead of photons being these independent things, they are now considered the exchange particle in this interaction. So forces are really an interaction between particles. Okay, so that's the idea. Like I said, we haven't been able to do this with gravity, although they have come up with a name for the exchange particle. It's called a gravitino. For the weak nuclear force, there is some exchange particles called the W plus, W minus, and the Z particle. Anyhow, this isn't particle physics, so we're not going to get too far into this. But the idea of these particles freezing out is that the energy, the amount of the temperature, right? The average temperature of the universe falls below a certain value where the pair production, doesn't immediately get, as soon as a fundamental particle is created and its antiparticle, the energy is not high enough, right? That's what it means to be frozen out, so that those particles will stick around for a while. All right, so that's the idea. And again, and as I mentioned in the last video, if this was a particle and an antiparticle, they tend to annihilate each other and form gamma rays, right? So they basically go back from being a particle, a piece of matter and antimatter, back into energy, right? So they, but of course we find we have to find that there has been somehow this slight asymmetry for matter over antimatter. So there's a little, in the very early universe, there was a tiny little bit. Some estimates put it at, 1 particle more. So, 1,000,000,001 particles of matter versus 1,000,000,000 particles of antimatter, and so all that becomes, the universe, the universe that we know of, the normal matter that we know of. All right. So anyhow, let's continue. So if we extrapolate back to the Big Bang, you run into singularity. But you might remember this guy that is very famous physicist who passed away not too long ago, although it's been a few years now. His name was Stephen Hawking. He was this absolutely brilliant physicist who did a lot of his work in the 1960s and 1970s. I mean, he continued to work throughout his life, and you might also recall that he was bound to a wheelchair, and he had a thing called a disease called Lou Gehrig's disease, which affected his muscles. In fact, he couldn't even talk after the 1970s. He actually had to have like a computer, and he would be able to move his hands, just a very slight motion in his hands, and eventually he couldn't even move his hands anymore. It was just he had to like move his eyes, and the computer would actually pick up individual words. He could scroll through and talk that way. I actually, believe it or not, got to see him in person a long time ago. This was actually back in the 1980s. He came to Caltech, and he was good friends with a guy who's actually currently still at Caltech. His name is Kip Thorne. Anyhow, the two of them always had these bets about black holes and so forth. Anyhow, Stephen Hawking was absolutely fascinated with singularities, and one of the main things that he did was to compare the early universe. He was the first one to do this, compared to the early universe to the singularity at the center of a black hole. Which led to some amazing breakthroughs, at least theoretical breakthroughs. All right, so this is, as far as physics goes, we can push back to this unbelievable 10 to the minus 43rd seconds after the Big Bang. So before that, this is an incredibly small amount of time, but before that, physics basically breaks down. And we think that we can understand what takes place after that amount of time. So that amount of time, this 10 to the minus 43rd seconds, has to do with quantum mechanics, and one of the founders of quantum mechanics was a guy named Max Planck. And so this time in the early universe is called Planck time. It's a tiny little fraction of a second, right? As it says here, 10 to the minus 43rd seconds. All right. Anyhow, so again, before Planck time, all bets are off. We have no idea what actually took place. And another thing, I think, if you think about what happened before the Big Bang. I mean, that's a lot of, so inevitably this kind of question comes up in class, and it's a natural human question, certainly. The thing is, physics can't deal with that, right? There's with science in general, of course, you have to have some kind of experimental evidence to lead your thinking, right? I mean, you might have some great ideas, great theories, but you still have to perform some kind of experiments that show that you're on the right track. And so it turns out, it's kind of like the question of what's as far as the Earth is concerned. So if let's say you get to the North Pole and you say, well, what's north of the North Pole, right? It becomes a meaningless question. And some scientists think that asking questions about what happened before the Big Bang is a meaningless, in the sense that science has no ability to answer that. But we can deal with the universe after this short amount of time called Planck time, after 10 to the minus 43rd seconds. That's pretty good. You start there. All right. So of the four, at some time after this, gravity, of course, is the first of the forces, of the four forces. Let's go over the forces again. I think we're going to do that in just a moment in these slides. But the four forces in modern times are gravity, the strong nuclear force, which binds the nucleus together, the weak nuclear force that is responsible for radioactive decay, and of course the electromagnetic force, which is responsible for all forms of electromagnetic energy. And of course charges, the charges that bind the nucleus together and bind the atom together and things like that. All right. So anyhow, gravity, we think, if gravity is so different than the other three forces. The other three forces can be described with quantum mechanics, whereas gravity is described by Einstein's theory of general relativity, which is quite different. It's very, very different than quantum mechanics. And people have been frustrated with that for a long, long time. We would love to have this quantum theory of but that eludes us at the moment. There's been some progress in that, and there's an area called string theory. You probably have heard of that. And that's actually a very strong candidate for. And you got to understand, it's completely theoretical. We don't have any kind of evidence that string theory is correct. The mathematics works out really well to be able to incorporate gravitation, but as far as we know, it's still just a theory. Until you get actual empirical experimental evidence, it's what we call just a theory. All right. Now, grand unification theory is actually a theory that has some evidence that it's true, and that evidence, by the way, is that the weak force, the weak nuclear force, and the electromagnetic force at really high energies. I think it's we'll have to. I forget exactly what the energy is. If I remember, it's something like 10 to the 15th. Anyhow, 10 to the 15th Kelvin. Anyhow, those. In our experiments have shown that they unite as a single force, and we think that even higher energy, the strong nuclear force will unite as well. All the equations work out again, but you have to actually experimentally do that, to prove this. But our particle accelerators just aren't strong enough quite yet. Maybe sometime in the future. Anyhow, collectively, this unifying, finding a unifying theory is called grand unification theory. So it's sometimes abbreviated GUTS, of course, for grand unification theory. There's GUTS. There's another thing called SUSY GUTS, which has to do with supersymmetry. supersymmetric grand unification theory. So there's lots of fun acronyms when you get into particle physics. All right, so the next era that we're going to discuss. So there's the grand unification era, where all the forces, or gravity peels off first, and then all